In the Week 4 physics lab, we were given the task of demonstrating the conservation of energy in a system during an energy conversion. The conservation of energy is a fundamental principle in physics, which states that in a closed system, the total amount of energy present is constant. It emphasises that energy can neither be created nor destroyed, only converted to different forms. In order to demonstrate the conservation of energy in a particular energy conversion, we had to come up with a way of quantitatively measuring each energy type and then showing that these measurements agreed. To approach this task, we decided to set up a simple pendulum to demonstrate and measure conversions between gravitational potential energy and kinetic energy. A simple pendulum is a weight suspended from a pivot such that it is able to swing freely along a circular arc. When a pendulum is swung to its highest point, it is stationary, so has zero kinetic energy. Instead, all its energy is in the form of gravitational potential energy. Gravitational potential energy can be described by the formula U of G equals m times g times h, where m is the mass of the weight, g is the acceleration due to gravity, and h is the distance it is raised above the ground. When a pendulum is swung to its highest point, h is maximised. Since m and g are constant, gravitational potential is therefore maximised when the pendulum is at its highest. As the pendulum swings from its highest point, h begins to decrease, in turn causing gravitational potential energy to decrease. As the pendulum lowers, its speed picks up. Kinetic energy is directly related to speed, given by the formula Ke equals a half of m times v squared. Hence, kinetic energy increases as the pendulum lowers. When the pendulum reaches its lowest point, its speed, and thereby kinetic energy, is maximum. When the pendulum begins to move upwards again, its speed and hence kinetic energy decrease, while its height and hence its gravitational potential energy increases. By the law of conservation of energy, neither the gravitational potential energy nor kinetic energy can be lost or gained by the system. The pendulum obeys this by producing a constant balance between kinetic energy and gravitational potential energy, such that when one decreases, the other increases. Hence, the total energy of the system, kinetic energy plus gravitational potential energy, always remains constant. In order to model a simple pendulum, we used string to tie a small metal weight to a retort stand. We recorded the mass of this weight using a scale, which gave us a mass of 119.7 grams. Since the scale only gave us a reading to one decimal place, this measurement had an uncertainty of plus or minus 0.05 grams. This is because such a scale would be equally likely to round a difference of 0.05 up or down. We decided to measure the energetics of this pendulum over the course of one single swing, from one side of the pendulum to the other. Using a smartphone, we filmed this swing. We then used a software called Video Physics by Vernier to determine the approximate position and speed of the pendulum at each frame of the video. Each frame was approximately 0.035 seconds apart. This software provided 4 datasets: the weight's position in the x direction, position in the y direction, velocity in the x direction, and velocity in the y direction. Similar to the scale, the software's roundings to 2 decimal places made its limits of accuracy plus or minus 0.005 for all 4 of these datasets. Plotting the y positions against the x positions, we were able to map out the path the weight took during its swing. However, the limits of accuracy of the software we used limited how accurate this map was, causing our map to have similar apparent y values for multiple values of x. We were further able to utilise this data to calculate both the kinetic energy and gravitational potential energy of the weight at each frame. The kinetic energy formula, Ke equals a half of m times v squared, requires us to know the square of the speed of the weight. From our data, this could be determined by applying Pythagoras' theorem to the x and y velocity vectors, whereby v squared equals x dot squared plus y dot squared. The gravitational potential energy formula, U of G equals m times g times h, requires us to know the acceleration due to gravity as well as the height of the particle. Using a local gravity calculator, taking note of the exact latitude of the physics teaching building, and noting the approximate altitude of Canberra with an uncertainty of plus or minus 20 metres, we were able to estimate the acceleration due to gravity experienced by the weight with an uncertainty of about 0.0001. The height of the particle could be simply obtained as simply just the y position of the pendulum. Using an Excel spreadsheet and considering measurement uncertainties, these calculations were made for the minimum values, maximum values, and the average of the two. Plotting both gravitational potential energy and kinetic energy over time, we were able to see that for all 3 uncertainty calculations, an increase in one of the energies paralleled with a decrease in the other. This hence allowed us to prove that there was in fact an energy conversion between kinetic and gravitational potential in our pendulum. Further, plotting the sums of each energy type for the 3 uncertainties, we can see that it is reasonably likely that the total energy of the system remained constant the entire time. This data did, however, produce a slight upward trend, implying that the system may have gained energy. This is likely attributed to the limits of accuracy the software provided, as well as a possible pushing of the weight as it was released from our fingers. Conclusively, the simple pendulum is a prime demonstrator of the conservation of energy during energy transformations. By modelling a simple pendulum and measuring the movement of the weight, we were able to demonstrate that an energy transformation did occur and deduce with reasonable confidence that energy was in fact conserved.